Hi, judges. My name is Xaneva Elorriaga George. I'm 22 years old from Toronto, Canada. I'm a continuing student at UC Berkeley, and my aspiring startup is Meduse Biolabs. In the last decades, the versatility of plastic for industrial applications has been invaluable for the food industry. However, the widespread use of plastics has led to environmental and human health issues that are now of growing concern. Specifically, there is evidence of bioaccumulation of microplastics in nature, in the animal food chain, as well as in human. Up to 70% of people have been found to carry microplastics in the body at the cellular level. Microplastics from single-use food and water containers are of particular concern, as these plastics can be directly ingested, leading to metabolic, inflammatory, and oxidative damage to the human body. With plastic production set to triple globally by 2060, bioplastic is a promising emerging industry, yet none of the ones on the market are widely used because they cost substantially more than conventional plastic, can't compare to its physical strength, and may not always be more ecological when in the typical landfill setting. The terminology used to classify bioplastics remains obscure and unregulated, as compostable, certified compostable, and biodegradable can all mean different things, with undisclosed degradation times, and not all degradable in the same types of facilities. These products may be labeled degradable, oxo-degradable, and oxo-biodegradable. These plastics are conventional plastics with up to 30% bioadditives like starch, which does break down, however, leaves the 70% conventional plastic behind to eventually decompose into microplastics. So these are misleadingly labeled. Unfortunately, many bioplastic companies' environmentally friendly claims are greenwashing and lack unbiased third-party testing. While we applaud these innovations for certain uses, when it comes to single-use plastics, we think they're a band-aid solution. With only about 9% of plastics recycled annually, it's clear that if plastic producers depend on the proper disposal habits of the individual, our collective environmental goals will never be achieved. With these shortcomings we found in our bioplastic research, we realized a new alternative was needed, so we went about developing an ecologically interesting material. We decided to question the need for industrial-grade strength materials for single-use applications. When will my takeout box be subject to hundreds of degrees and high-strength situations that could destroy its integrity, spoiling my late-night Uber Eats? Take a plastic water bottle, for instance. I can easily poke a hole in it because it isn't physically indestructible, but why is it structurally undying? If it no longer serves its purpose after one use or after it is physically impaired, why should single-use plastic be so resistant to degradation? Since we believe that once something no longer serves you, it shouldn't remain intact, we realize that there could be another means that is more effective than biodegradation. So we want to create a hydrogel. Hydrogels are typically used in soft applications such as contact lenses and body implants, but have never been thought of as a plastic alternative. A childhood memory of the thick gummy cap of a beach jellyfish dissipating into thin air a few hours later brought about the creation of Meduse Biolabs. We want to leverage this process called deliquescence, a solid material's attraction and absorption of moisture in the air, causing it to gradually disintegrate into natural parts and liquefy back into water without any addition of heat. We hypothesized that with some synthetic biology, we could create a hydrogel for industrial application that would deliquesce by biomimicking the mesoglia of a jellyfish, the extracellular jelly-like matrix that is only solid when submerged in water. By keeping our hydrogel submerged in water within the outside layer, what we call its epidermis, we can make it so that no external conditions are required to dissolve it once it is drained of its aqueous environment, similar to how a virus dies within seconds outside of its host. While industrial plastic innovation typically focuses on structural integrity, leading to the material's immortality, and ecological materials are created to have short lifespans or mortality, our competitive advantage is giving the user the ability to control when it degrades, what we call biomanipulation. When the user impales the material, the encasing layer would instantly unravel and the biocomposite could resume its finite lifespan. If this material would successfully deliquesce in a matter of hours, it could make our material the fastest degrading semi-rigid material on the market. Essentially, our research question is, can we achieve the same usability as semi-rigid plastics with a hydrogel while maintaining biocompatibility and achieving the fastest degradation rate on the market incited at your control? With the 25K, this could be a possibility. I'm in the stages of beginning a biomaterials co-op at the Gunther Lab at the University of Toronto, where I would be extruding collagen filaments at 2 microns thin for vascular tissue repair and presenting this work in a poster to the mechanical engineering department. So this experience will help solidify the pre-analytical design phase, which I'd be able to apply to the biomaterial project. We would use this money to create a materials algorithm with programmers, rent out lab space, bring other materials engineers on board, purchase materials, and develop a minimum viable product. As a startup in the complete pre-seed stage, getting funding in order to develop an MVP is very unlikely. So with this 25K, this could be life-changing. So if you think water is the new plastic, please join us on our journey to making degradability programmable. Thank you.